In this video, we're going to learn about the method of separation of variables, which is going to be our first major method to be able to actually solve a differential equation. Now, when I first introduced differential equations, we talked about the exponential growth equation, an equation where on the left-hand side, there was a rate of change of y, a derivative, and on the right-hand side, it was proportional to the value of y. And this exponential growth equation models a whole lot of real-life phenomena. Any time where the rate of change is proportional to the amount that you actually have. For example, in a pandemic, when we're in the early days, and the growth rate is just proportional to the number of people who are infected. Or in a bank account where the growth rate, if it's compounding continuously, is proportional to the amount that you have, perhaps 5% interest as time goes on. And so this differential equation comes up in all sorts of places. But when we previously talked about it, I just gave you the solution. I said the solution is y is some constant times e to the kt. And you could verify that yes, it was a solution by plugging it into the left-hand side by taking the derivative, setting that equal to the right-hand side. But where did this come from? That's what I'm going to answer in this video. So what we're going to do is this method of separation of variables. And the first thing I'm going to do is I'm going to take the y on the right-hand side and I'm just going to divide it out and put it on the other side. And the reason I'm doing this is that now on the left-hand side, there's everything in terms of y and the derivative with respect to y. On the right-hand side, there's nothing to do with y at all. Now I'm going to take an integral of both sides with respect to t. I'm allowed to do that. I'm allowed to add the same thing to both sides. I'm allowed to multiply both sides by something that's non-zero. I'm allowed to integrate both sides with respect to t. I can do the same thing to both sides of an equation. So I can integrate both sides of an equation with respect to t. And then I notice that I have on the left this dy dt dt. And it's tempting to just say that I can cancel the dt divided by dt, which is sort of a convenient fiction, because what we're actually going to do is define something new called dy. dy will be defined to be dy dt dt. This is just a change of variables. So now on the left, I have an integral entirely in terms of y, and on the right, an integral entirely in terms of t. Let's do those integrals. On the left, the integral of 1 over y is the logarithm of absolute value of y. On the right, the integral of k becomes kt. And then I always have to remember to add the plus c, my additive constant of integration. Okay, so we have a solution here, and we actually can solve it a little bit better. I'm going to take e to the power of both sides to get rid of the logarithm. So on the left, e to the logarithm of absolute value of y, that's just going to cancel to become absolute value of y. And then the same thing on the right. We're pretty close to being done here, but one more manipulation. E to the kt plus c, when you add up in the exponents, that's just the same thing as multiplying by another copy e to the c. So e to the kt plus c is the same thing as e to the kt times e to the c. And then I'm just going to relabel e to the c as something called c tilde. Basically, my additive constant up in the exponent has now become a multiplicative constant. So c and c tilde are slightly different, but either way, it's just some constant. I also have dropped the absolute value signs. This was just because exponential is always positive, and so I don't have to worry about when y is negative. And so now we've gotten the same solution that I've asserted to you previously by this method of separation of variables. Okay, now let's step back and do this a little bit more generally, because this example was actually so simplistic, it might miss some of the complexities of this method. So generically, what I want to talk about is when you have a first-order differential equation, so a single derivative y prime, and that can be written as the product of some stuff entirely in terms of t, some function of t, and some stuff entirely in terms of y, some function g of y. If it can be expressed as a portion that's a function of t and a portion that's a function of y, and those are just multiplied together, then you can use separation of variables. And here's how the method works. We'll do exactly what we did before. Everything with respect to y has been moved to the left now. So on the left, I have y and derivatives of y. That's what's appearing on the left. On the right, I have things in terms of t only. For now, I've got a dy dt, and I'm going to leave that as one object, one derivative. I'm not going to try to separate it just yet. I'll talk about that a bit more in a moment. So on the left, it's like y and the derivative of y. Okay, now I have an equation. I'm going to integrate both sides of that equation with respect to t. So the integral of 1 over g of y, dy dt dt, is equal to the integral of f of t dt. I've integrated with respect to t on both sides. I'll do the same trick as before. I will define the differential dy to just be dy dt dt, and so I get to replace that. And now I have an integral with respect to y, and an integral with respect to t. As a matter of preference, what a lot of people actually do is just separate out the dy and the dt and move them to the opposite sides of the equation at the beginning, and then just integrate with respect to those two variables. That's fine, that's a really good shorthand to do. In fact, it's what I do as a shorthand. But it is still good to know that what we're sort of properly doing is integrating both sides with respect to t and then doing a change of variables. If you want to separate out the dy and the dt early on, that's okay with me. Either way, I have an equation of two integrals. I might be able to do these integrals, I might not be. Integration can sometimes be hard. But if I can do those integrals, I'm going to get some equation in terms of y and t, but no longer in terms of y prime. It's an equation of y and t, and that will be my solution to the separable differential equation. Okay, so let's look at a slightly more interesting example here. This is now y prime is equal to xy divided by y squared plus 1. Our first question is it separable? And yes, it is. We have a portion which is just the x, and that is multiplied by a portion which is some function just of y, the y divided by y squared plus 1. It's a multiplication of these two separated components. So let's apply the methodology. First of all, I'm going to divide through. So dividing through by the function of y gives me y squared plus 1 on the top divided by y times dy, and then on the right-hand side, x dx. Here I have now done and taken the dy dx and sort of, as a convenient fiction, just separated it to both sides. So it's all y's on the left and all x's on the right. Okay, so now I integrate both sides, which is great. And now it's just a matter of doing those integrals. So on the left-hand side, okay, y squared divided by y is just y. It integrates out to y squared divided by 2. 1 over y integrates to logarithm of the y. X integrates to x squared divided by 2. And then, of course, I always have to do this. I have to add that plus c. Now, this solution to the differential equation is maybe not the nicest thing you've ever seen, because what it is an implicit solution. I don't know how to solve this and make it y equal to a function of x. I haven't nicely solved it the same way I did with exponential growth, which said y equals constant times e to the kt. Here it's some equation that governs the relationship between y and x here. By the way, I changed all of this to be an integral with respect to x. Sometimes our independent variable is x or t. We should be able to do both. But either way, I have this implicit equation that defines them. And sometimes that's just all you get, then that's okay. However, there's even one more complication, which is that there is another solution to this differential equation, one that is not written in this format. It's pretty simple. It's just called y equal to 0. We sometimes call this the singular solution. I mean, the derivative of y equal to 0 is just 0. That's the left-hand side would be 0. And if I plug in y equal to 0 on the right, I'd get 0 equal to 0. So this is a solution. But y equal to 0 is not in the form of this implicit equation that I have. And this is a big challenge with differential equations. Sometimes you get solutions, but then there are even more that are not discovered by the methodology that you've chosen. And this is going to be a big theme that we have to think about and resolve and come up with some theory to discuss as we go on in our course. To get a little bit of a sense of what's going on with this implicit equation, I've come in here and I've typed it in and graphed it for the specific value of c equal to 0. And what you can see if I come here and change the value of c is that it all looks like the same basic type of shape. But depending on where you start, depending on an initial condition, it would tell you which specific value of c you're in, and thus what specific plot are you going to be on. And then it's also sort of worth noting what's going on with the singular solution y equal to 0, which has not been plotted here, but if I wanted to, I could come along and add an extra equation for y equal to 0. Well, if I was to make c be very, very negative, as you can see, the more negative c gets, the closer to that singular solution it becomes. This sort of makes sense. If the c value is a very large negative, how would you get a negative on the left-hand side? Well, you'd have to be taking the logarithm of a number that was very, very close to 0. And that's why, as you have c going very, very far to the negative, y is going to be approaching 0 in some sort of limiting sense. But this y equal to 0, the singular solution, nevertheless looks substantially different than the solution to this implicit equation at any given point. And these types of relationships between the solutions that you find in so-called singular solutions are quite common in differential equations.